Before we return back to CERN and the Large Hadron Collider, I have one question about physics beyond the Standard Model and the Higgs Boson. And I'm wondering whether, because I've never heard this before, so I must be wrong with my intuition somewhere, whether the Higgs Boson is at all central to efforts at unifying gravity and quantum mechanics, since the Higgs Boson is what gives fundamental particles mass
Mm-hmm.
in the Standard Model, and gravity, at least at our macroscopic level, is very much connected to mass.
Yeah, but no, I mean the answer is no. Actually, really, it's not really that central, and that's because gravity itself doesn't really distinguish between energy and mass. So the fundamental object in general relativity is the energy momentum tensor, which has terms that are due to mass. But from a point of view, from a long way away, gravity doesn't care whether your energy is in the form of protons and neutrons or photons or whatever. So if they're over there, they're behaving like energy, and that's what distorts space-time. That's what creates gravity. So it's not really. I mean, there were people that before the LHC turned on. It's less interest now. I think because we found the Higgs. There were people trying to avoid the need for the Higgs by saying that actually gravity comes into play much earlier than we thought. There are extra dimensions of space-time. I think you mentioned them before with neutrinos, but you could have had extra dimensions of space-time that gravity is sensitive to, but which once you get to the energy of the LHC, you can actually probe. And these dimensions are present in string theory, but in string theory they're way out of reach of the collider. But if you brought them down to LHC energy, you could maybe get away without needing a Higgs at all. And people, for various reasons, people didn't like the idea of there being this fundamental scalar. So these extra dimension models, which would have explained quantum gravity at some level, would have also been a way to avoid the need for a Higgs as well. But now we've found the Higgs, of course, that's a lot less interesting because we know it's there. I think it's not really central to quantum gravity investigations, at least at the moment. It's still, I mean, I have to say, on the timescale of physics, it's still an important new piece of information that people are still digesting. So I wouldn't want to bet too much money that it won't actually turn out to be important in that. But at the moment, I wouldn't say it's central to those investigations now.
Well, what you just said raises a new question for me. You said it's relatively new in the timescale of physics, but it doesn't seem relatively new in the timescale of quantum physics, in the sense that it's been theoretically around since the 60s, and a lot of people have been very certain that it's there.
Yep.
So in what sense is it new? Is it that the discovery a decade or so ago has resulted in more work empirically that needs to be done?
Yeah, it's sociologically interesting, actually, because you're absolutely right that a whole bunch of theorists have been assuming it was there for a long time. And the actual knowledge that it's really there has had a big impact on the field, even though you might have thought it wouldn't have done. And well, there are a couple of reasons for that. One is that, there's a certain kind of physicist who, when there's a real new phenomenon to get your teeth into, then you start doing more precise calculations of it and things, and that can throw up more insight. Another is that they kind of knew it was there, we didn't know what the mass was, and it turns out the actual knowledge of the mass is important and interesting, and might be on the cusp of whether, for instance, the universe is metastable or stable, and maybe that's telling us something interesting about how the universe evolved.
Sorry, did you say metastable or matter stable?
Metastable.
Okay.
I mean, obviously the universe has to be either nearly stable or completely stable, because otherwise it wouldn't be here anymore. So metastable just means that it's practically stable, but it in principle might not be in the very, very long run. And the Higgs mass is sitting somewhere, implying that it's right on the borderline between the two, actually, which is probably insight. There's probably an insight there if we could work out what it meant. So those are a couple of the reasons. And the other reason, maybe a more negative reason for it having an impact, is that a lot of theorists also thought supersymmetry or some other beyond the standard model idea would show up at the same time as the Higgs, and that just hasn't happened. So now people have to take the standard model a lot more seriously than they did in some ways. I mean, I think a lot, if you'd have asked theorists in, I don't know, 2008, 9, just before we turned on the LHC, what do you think will happen? I think most of them would said we will find the Higgs, but we will also find a lot of supersymmetric partners of the other particles as well. And we haven't. And we may still, they may be hiding somewhere a bit less obvious, but it's looking less and less likely. And that's had a huge sociological impact on the field in general, theory and experiment. And people are, there's still some diehards thinking there's still possibilities that supersymmetry will be there, but it's nowhere near as monolithically the overwhelming favored theory that it used to be. And certainly you have to take the idea that the standard model might be a very, very good effective theory on its own with no help from beyond the standard model for quite a range of energy. Right now, it seems to be that way. So all these things have subtly changed the way people look at theoretical physics, and I say that they're kind of 10 years is not. It's not that recent. It's not that long ago, but that's the discovery that did that, not the events in the 60s when the theories postulated it. When it was postulated, it was just one theory idea amongst a zillion others, right? It's only because that's the way nature behaves that it's become super interesting.
When you said metastable, you really got my attention, and I was thinking, second order stability or abstract stability, but not. It's kind of less exciting, your metastability, but it does raise the interesting question to me about, or that sort of relates to the Barber Paradox. So who shaves the barber in the town where the barber shaves everybody who doesn't shave themselves? But the question is, what gives mass to the Higgs boson?
Oh, the Higgs does, though. That's okay. It's
okay.
The standard model within that is completely self-consistent, and it builds that in as well. This is the amazing thing, right? We've got this completely internally consistent theory now, which doesn't explain dark matter or dark energy or gravity, but within its own purview, it's completely self-consistent and doesn't need anything else to help it out. It's kind of amazing. Mm-hmm. The stability, just to be maybe it's worth just saying another word about that. So we're saying, I talked about the wine bottle, and you've got the rim of the wine bottle, which is a local minimum where the marble will end up, and that's where the universe is now. And when we talk about whether it's metastable or stable, if that's really a global minimum and really the lowest point the marble can ever get to, then that makes it really stable. But if the wine, maybe it's better to go to the Mexican hat, so it's like that kind of thing instead. If the hat has got another lip down here with a lower vacuum, and we're in a kind of local minimum, but actually we could tunnel through to a different minimum, there's another global minimum somewhere else. That's what I mean by metastability. And it means the universe could at some point tunnel through to a different vacuum, a different minimum. But we know that if that happens, it has to be far enough away that the probability is so low that it hasn't happened in 13.8 billion years. So it's not going to affect our lives in any way. But from the point of view of how did the universe evolve and why is it the way it is, it might be a big clue as to what's actually going on. It's the other thing that the model for this is that why sand dunes always got the same angle? Why do they always form at the same angle? That's because that's the cusp between stability and instability. The sand piles up until it falls down.